Hi there, Science 9. So today we're going to cover Lesson 5, Ocean Currents. Rather than have me write stuff on the board, I'm going to show you guys some websites that relate directly to the topic. So yesterday you would have seen or maybe written down maps a little bit like this. What this shows is the prevailing winds that go across the surface of the earth. Strongly recommended you watch this video right here to understand a little bit about how that works. But bottom line is the earth is a sphere that is continually rotating. So you know the sun rises in the east and sets in the west, and so this is explained by the fact that the earth is rotating that way. Imagine that the sun here is okay, imagine the sun. Imagine you're the sun right now. And there's BC right there at the corner of the map. Okay, Earth is rotating. Sun just rose in smithers, all right? The Earth rotates that way. Now, if the Earth did not rotate, warm air would continuously be rising at the equator and expanding and then moving away from the equator towards the poles and sinking at the poles in a kind of a spiral that would look like this in cross section. But because the Earth is rotating like that, the air gets deviated and makes spirals across the surface of the Earth, creating the prevailing winds, which near the equator move from east to west as the Earth is rotating. There is, however, maybe a bit of a counterintuitive flow that happens in the temperate regions where it creates a kind of a vacuum, what's happening around the equator, and actually pulls air back towards the east. And then, of course, as I said yesterday, you again have that same pattern around the poles where, again, air is moving at the poles from above, clockwise direction. In other words, from the east to the west, just like at the equator. So this is prevailing winds. What we're looking at for today is prevailing ocean currents. Now, of course, ocean currents can't go across the land for obvious reasons, but the key point for ocean currents is that the ones that are at the surface do respond to the prevailing winds, and you get very similar patterns. Have a look at this. Compare this here, these winds going in this direction, with these currents right here. You see the currents, the surface ocean currents are going in the same way here around the equator here in the Atlantic, and the equator here in the Indian Ocean. And also, as you get into these temperate latitudes like the United States, southern part of Canada, we see these patterns where the ocean surface currents are twisting back towards the east from the west. In other words, you get these great big twists, these whirlpools. What they're actually called is gyres, G-Y-R-E, which basically means a giant spiral. A strange and really not very good consequence of that is that the air, the surface of the ocean in the middle of the gyre is not moving very fast, if at all. I mean, yeah, it can move a little bit, but overall, it tends to move a lot less. And so solid things that can float tend to collect in the middle of the gyre. So you get this thing, for example, in the North Pacific, but also it's starting to form elsewhere, this what's called a garbage patch. I'm going to just see if I can get an image for you. Well, that wasn't hard. So this is a little bit like things will look if you're in the very middle of the Pacific Ocean. You don't find a uniform patch of garbage because we're talking about an area the size of Canada or larger, but you find a lot more garbage collecting there in the middle of the ocean, thousands of kilometers, literally thousands of kilometers from any land. It just gathers there because the water is so still. And this again comes down to these ocean currents right here. Things are moving around in here, but they tend to kind of slow down in here, and then the middle of the gyre, well, they're effectively stopped if it's in the middle of the gyre and everything's moving around it. There is a patch of garbage like that has started to collect in the Pacific. Not too surprising, given that the big producers of garbage that ends up in the water are Indonesia, I think the Philippines, and China for certain other Southeast Asian countries. It's not like here in North America we're innocent of it, but if you look, for example, at the Philippines, they have a very high coastline, and their infrastructure for taking care of garbage may be not as good as ours with a very high population density and not much land to work with. And so naturally, garbage ends up in the ocean, and of course, garbage is tossed off of ships. This might sound like a really abstract problem, doesn't look like it's doing anyone any harm over there, but it does do a great deal of harm to wildlife. There was a guy who did he was a photographer, a wildlife photographer, and he went to a place called Laysan Island near Hawaii, and he started to see these Laysan albatrosses that live on that island where just the chicks would mature from their parents, but then the chicks could not leave the island because their stomachs were stuffed with plastic. Because what's happened is these Laysan albatrosses mistake the plastic for food, and they just gobble it up, and they feed it to their chicks. It's actually quite tragic. You see here, this Laysan albatross is accepting a stomach full of plastic from its mother. As a result, it's never going to fly, and it will die probably a very painful death. This comes down to our poor behavior when it comes to waste management, but also it comes down to these prevailing ocean currents. I thought something would be really cool in this discussion would be to look at some of these patterns of how this works, connecting the surface winds with the surface currents, because again, it's the surface winds above the ocean that control those surface currents. So here's what I showed you yesterday. This was a globe, and we see moving across the Pacific, we've got these winds moving from east to west, right? Because as the sun rises in east, it sort of leaves some of the air behind. By drag, the air doesn't move quite so readily as the solid rock. And so there's this natural flow from east to west of air, but then in the temperate latitudes, it gets twisted in the opposite direction. So that's what it looks like for wind. And I was like, hey, do we have one for ocean currents? And the answer is yes. It's really quite awesome. The same guy who did the one for wind did one for ocean currents. And you can see these are surface ocean currents. Let's see if I can zoom in on that. I was able to earlier. Okay, doesn't matter really. You can kind of, I want to do that. There we are. Okay, much better. So here's the Pacific Ocean, and we see same pattern, right? Let's look what's happening in the wind, for wind, the Pacific Ocean. There, that movement from east to west. And here, the ocean currents are following it. The ocean is flowing along the surface from east to west. But there's a lot of other stuff going on here. You have little eddies, like little spirals, like look what's happening off the coast of Hawaii right here. There's a kind of a set of spirals of water there. And in the middle of the ocean, it looks a little bit like a bowl of spaghetti where you've got these other kind of currents that are probably responding to local weather events. But here's something that's very important. Look what's happening here. The water, having flowed across the Pacific, reaches, it hits, this is Papua New Guinea, kind of churns off there. It probably heats up there because we're in the tropics after all. The land heats up a lot, and it goes up the coast of the Philippines, China, Japan, and it's being cast out into the ocean and cooling off. That's it. That's hugely important because the deal with water is water has what's called a very high heat capacity. It's very good at storing heat. If you take a cup of, say, hot coffee and you leave it sitting out in the room for, say, I don't know, a half hour, and you come back then and feel it, it's still pretty warm. If you heat up a cup of air and do the same thing, it doesn't have the same effect. The temperature from the air, the air does not store so much thermal energy as the hot water does, the hot water in the coffee. Water has what's called a very high heat capacity. So when water that is warm is flowing from the equator up against the coast of Asia and twisting back towards the east, having come from the east, it's carrying a huge amount of heat. In other words, this land off here off the coast of southern Japan can be a lot warmer because there's a lot of warm surface water that originally comes from the tropics, right? The ocean currents are a great way for the temperatures to distribute themselves across the more evenly across the surface of the Earth. If we didn't have the oceans, the poles would be much colder, and the tropics would be much hotter. Let's look at how that plays out in Europe. All right, similar pattern. Look at this, wind coming from ocean currents coming from the east going towards the west. They hit the Amazon Delta, which I find kind of interesting what's going on there. And I have other ideas to explain that I could get into, but won't right now. But look what's happening here. These currents are flowing across the northern coast of South America through the Caribbean. They hit Florida, which is very warm, Carolina, the Carolinas, whatever. Basically, we're hitting the eastern seaboard of the United States, and they kind of veer off, and they end up in the North Atlantic. So as a result of that, let's compare this here. We've got this point here off the coast of Newfoundland. We've got these warm ocean currents. This is happening right now. This is more or less real-time ocean currents that are happening right now off the coast of Newfoundland, the Maritimes area there. We've got this warm ocean current sending what was once tropical water into the northern Atlantic. And you can well imagine that that's going to be redistributing heat. The heat that was created at the equator is being sent towards the poles, making the poles warmer than they otherwise would be. So that's the way it works with surface ocean currents, is that they respond mostly to wind. Let's look at what's going on right here and see if I can get any closer. Good. All right, excellent, in fact. So look what's going on here. I have my theory as to why this is happening. First of all, those of you who are geography nuts are going to know that right here is the delta for the largest river in the world, the Amazon. Carries by far the most water of any river. Now you might expect that off the coast of the Amazon, you're going to have massive currents going in that direction, and it's going to be pushing the water of the ocean outwards in all directions because it's carrying so much water. But look what we've got right going on here. We have these ocean currents here flowing towards Brazil, and they look like they're getting sucked underwater. Look at that. From all these different directions, the surface water of the ocean is getting sucked underwater. Here's what I think's happening. I think that this warm, salty water is actually, or this salty water is flowing underneath the fresh water of the Amazon, because salty water has got a higher density than fresh water does, so it's going to sink in fresh water. But if you don't believe me, I've got a quick experimental demonstration I'm going to show you in a little bit. I do also want to talk to you a little bit about deep ocean currents. So they are very well explained in this video, the Jennifer Verduin video, How Do Ocean Currents Work. You should watch it. What we see right here, in fact, are these deep ocean currents. What they're called is thermohaline currents. If you look here at what's going on the ocean surface, it's clearly fast. They mean to communicate here that these currents are moving not as quickly as a river, but moving quite quickly in response to wind. The ocean currents that run in the deep ocean currents are much slower. They're not being pushed by the wind. They're just flowing slowly across the ocean floor. The natural question is, why are they doing that? Well, first of all, you're going to see in the video, when you watch the video, which I hope you do, that, of course, we have these shallow water currents, like this one right here. which is very similar to the prevailing current that you just saw. But look what's happening here. When these warm waters from the Caribbean get up to the area off Iceland, it turns blue, right? What's actually being communicated there is that water is sinking. Because what's going on here is this water here is, it's warm when it's over here, but having been warm, it's lost a lot of its, it's lost a lot of its water. It's evaporated. It's saltier than the water would be closer to the poles. When that salty water is carried closer to the poles, I gotta do something. When that salty water is carried closer to the poles, it encounters water from that at the poles has a lower salt content. Lower salt content water is actually what was I going to say? It's got lower density. Saltier water has higher density. So what happens is that salty water, as it's going north, also becoming cooler. It's becoming cold, and it's being colder as it arrives there. It's become colder, and it's losing that heat. And also being saltier, it sinks. And it's here that this surface ocean current becomes a deep ocean current. So, some of the water is going to keep circling around on the surface, but this water right here, this is a place where that water sinks, right here, off the coast of, I guess, Norway. And it sinks down here, and now this water here has become part of a deep ocean current. Look at this right here. These two cross because this one is on top of this one. They're actually going cross paths to each other, and they cross again. But here, this is a kind of probably a point of some turbulence because we've got water going this way, surface current going this way, and here we have a current underwater going deep in the ocean going that way. What this is called is the Great Global Conveyor Belt of ocean water. The surface currents are fast. That's the fast component of it. But these currents here, these deep ocean currents, are very slow. For a single droplet of water, if you can imagine a drop of water doing that, that circuit takes some 1,000 years for water to follow that complete circuit of the ocean conveyor belt. So that's what I want you to know about ocean currents, is that the shallow ocean currents are in response to the wind. And there's one other thing I wanted to mention is that ocean currents also act at a very short distance at the shoreline. Anyone who's ever been to the ocean knows that. As the ocean comes in and goes out, that's in response to gravity from the moon. That's the tides. But the long distance motion of currents is what I've shown you more about right here. So I hope that helps if you're getting some understanding of deep ocean currents versus shallow ocean currents. I'm going to sign off from a screen share, but I am going to show you a quick experiment. Okay, so remember the discussion of deep versus shallow ocean currents. I told you that the reason that water from the equator that's moved towards the poles sinks is because it's saltier and because it actually cools down a lot. It becomes very cold when it reaches the poles. It's in contact with a lot of polar ice for a start, like the ice pack, and that causes that water, chilled and salty, to sink down. Because cold water is denser, also salty water is denser. But I thought, don't take my word for it. Let's do a little experiment, a bit of a demonstration about that. The first one's going to be about water temperature. I'm going to put cold water on hot water and hot water on cold water. And we're going to see what happens in terms of which mix and whether it's possible to make one kind of water float on another kind of water. So I'm going to start with the hot water at the bottom. Before I start, maybe think about what you might expect to happen to this water. So we have it's color coded. Our hot water's red. Cold water's blue. Here we have this, looks pretty uniform purple color. Let's see what happens when we put the cold water at the bottom. Hot water on top. I don't know if you've ever tried swimming in a Canadian, like a cold Canadian lake in the summer, and notice that when you jump in, it's nice and warm at the top, but then if you try diving underwater, it's freezing cold. That point in between the two of them is called a thermocline. This is all explained by the fact that warmer water is, not only the fact that the sun is coming from above, but also because the warmer water is more dense. This denser water here has stayed at the bottom. When I mix it such that I put the warm water in first, that warm water rose and naturally forced a mixing between the warm and the cold. When I put the cold water in first, this denser cold water in first, it stayed at the bottom. In fact, when I feel this here, it's very warm right here. You guys can't, but this is hot down here, and I can still feel the cold of this water. This warm water is sitting on top of this cold water, and is perfectly happy to do that because the density of the warm water is lower than the density of the cold water. Things that have a higher density are going to tend to settle towards the bottom. So there's a thermocline, or a bit like an icy lake to swim in the summer. You stay up here. If you dive down here, it's really cold. Let's look what happens when we compare salty versus not salty water. First of all, I'm going to put our cold water at the bottom. I'm sorry, our not salty water at the bottom. For this one, I'm going to put the salty water at the bottom. So I've mixed a whole bunch of salt into this. I'm going to pour salty on not salty, and I'm also going to pour not salty on salty. First of all, salty on not salty. And again, think about what's going to happen. Okay. Now we're going to pour the not salty, on the salty. To me, this never gets old. We see in this case right here, for this water I've just mixed, that the water with low salt concentration, which is fresh water, floated on the surface. Versus this water here that I just poured, we have this mixing where the salty water sank to the bottom. When I put the salty on top, it sank to the bottom because the salty has higher density. So the overall finding is fresh water floats, and also that warm water floats. And when you put when you put cold water on warm water, the water's going to sink and mix. When you put salty water on fresh water, the water is going to sink and mix. And again, these are processes. That sinking is what happens in the Arctic and wherever we've got warm water flowing into a polar region and encountering that pack ice. It chills down, it's got a high salt content, and it sinks. But other surface water is always coming by to replace that water from the tropics. As a result, you get deep ocean currents that actually are moving back away south from or back towards the tropics, but very slowly. So we have this fast process of surface ocean currents, and then this very slow process that's driven by differences in temperature and saltiness that determines the flow of the deep ocean currents. They're both extremely important for carrying water within the ocean. And where water goes within the ocean, because water has a high heat capacity, it carries lots of heat around, has a massive effect on our climate as well. So I hope that clarifies some concepts and maybe helps you develop some new understanding about ocean currents.